Jai Hind. So today's topic is Zener Diode, and this topic has been taken from the subject Fundamentals of Electronics Engineering. So basically, Zener Diode is a special type of diode designed to reliably allow current to flow backwards when a certain set reverse voltage known as the Zener voltage is reached. So basically, Zener Diode is a PN junction diode, heavily this is our PN junction diode. So when PN junction diode is heavily doped, then it is called a Zener diode. And Zener diode always operated in the reverse bias region. So some Zener diode have a sharp, highly doped PN junction with a low Zener voltage. In this case, the reverse conduction occurs due to the electron quantum tunneling in the short space between P and N regions. This is known as the Zener effect. So basically, if we operate the normal PN junction diode in forward bias, so it will be working like in this way, like this is the voltage and this is the current, and in reverse bias it will be like this way. So this is the reverse bias region and this is the reverse saturation current. So in Zener diode, this is the symbol of the Zener diode, this is the symbol for the Zener diode. So if we operate, and this will be always operated in the reverse bias condition, like in this way. So if we operate Zener diode in the forward bias, like this is our Zener diode, and if we forward bias this Zener diode like in this way, this is a Zener diode in forward bias, so it will be behaving like a normal PN junction diode, And if it is silicon, it will be conducting at 0.7 volt, and if it is germanium, it will be conducting at 0.3 volt. And now this region is actually the breakdown region, and this is voltage is the breakdown voltage. And if the Zener is operated in the reverse bias and this voltage is less than the breakdown voltage, this V is less than the breakdown voltage, means the Zener is operated in this region. So in this region, Zener will be acting as an open circuit. If the Zener is operated before the breakdown voltage, then in this region it will be acting as an open circuit. And if the Zener is operated in this region, that is V is greater than VB, so it means it is operated in the breakdown region, and in that case Zener will be replaced with the VZ volt, like this is a Zener, and it will be replaced with the minus plus VZ. So these are the some terminology that we have to remember, like this is the equivalent of, okay, this is a VZ potential diode, Zener diode will be replaced with Zener, and this will the open circuit, and here it will be operating as a normal PN junction diode. Okay, so to diodes with a higher Zener voltage have a more gradual junction, and their mode of operation also involves the avalanche breakdown. So avalanche breakdown also occurs, it occurs like this is the normal PN junction diode. So at this stage, this is the Zener breakdown, and for greater than 8 to 9 volt, it is the avalanche breakdown. Zener breakdown basically occurs due to the high electric field, and avalanche breakdown is the occurs due to the impact ionization. Due to the kinetic energy of the electrons, they collide with the atoms and some new electrons are generated, and this process is multiplicative. So Zener diodes are optimized for operation in the breakdown region, and one of the major application of the Zener diode that it can be used as a voltage regulator. Voltage regulation is a major application for the Zener diode. Voltage regulation means like we have resistor, and this is our Zener, and this is our load RL, and this is R, and here it is power supply plus minus Vs. Okay, so this is the series resistance that is connected with the Zener diode. So voltage regulation means like we have to maintain the voltage across this RL constant, like VL is the voltage. So this VL should remain constant either your Vs may be fluctuating, your RL may be variable, but VL must be constant. So this is the this is voltage regulation, and this voltage regulation can be achieved with the help of Zener diode, because Zener diode, like the if the Zener diode comes in its breakdown region, then the voltage across this RL will be constant. So we have to find the voltage across this Zener, and this voltage would be equal to RL upon RL plus RS multiplied by Vs. And if this V is greater than Vz, Vz is the breakdown voltage of this Zener, then this Zener will be working in this region, breakdown region, and it will be replaced with the plus minus Vz potential, and in that case VL would be equal to Vz. So here whatever may be the value of Vs, the voltage across the RL will be constant, that is the VL. Okay, so this is how, if we use the Zener diode in the forward bias region, and if it is a silicon diode, it can be replaced with 0.7 volt, and if it is operated in this region, then it will be open circuit, and if it is operated in this region, it will be replaced with the plus minus Vz volt potential. And there are three cases with the Zener diode. So first case is when Vi and RL both are fixed. So this is the diagram for the case first, that is Vi and RL both are fixed. Vi and RL both are fixed means, like this Vi, that is the input supply we are applying, it is fixed, and this RL is also fixed. And Vz, this is the Zener diode that we have applied. So for finding the output voltage, what we have to do, we have to find the voltage across this Zener diode. So for that purpose, what we will do, we will open circuit this, and this circuit will be like in this way, RL, R, and this is plus minus. Okay, so this is Vi, and now we have to find the voltage here. So this voltage will be equal to RL upon RL plus R. We can also write it as S also, so leave it. So V is equal to RL upon RL plus R. Now if V is greater than Vz, this circuit will be replaced with the Vz potential. This is Vi plus minus Vz, and this is RL. Okay, so in that case VL would be equal to Vz. So this is the case when both Vi and RL are fixed, and if second case is there, this is the first case, and if second case V is less than Vz, so in that case diode will be open circuit, open circuit. Okay, and in that case, okay, now we will see the second case when V is less than Vz. So when V is less than Vz, in that case diode will be open circuit, and the voltage will across RL will be equal to, VL would be equal to RL upon RL plus R Vi. So in that case output will be this much that we have calculated, and if V is greater than Vz, output will be equal to VL is equal to Vz. So this is the same that I have done in the previous slide. Here we have calculated the voltage across this diode, that is equal to V, and the value of V is RL Vi upon R plus RL. So if this V is greater than Vz, the Zener diode is on and the appropriate equivalent model can be substituted, and if V is less than Vz, the diode is off and the open circuit equivalent is substituted. So this is the this is how VL is equal to Vz and Iz is equal to IR minus IL. We can find the value of Iz, this is IR, and this is IL. So IZ is equal to IR minus IL. IZ is the current flowing through the Zener diode, and the power dissipation across this diode would be equal to PZ would be equal to VZ multiplied by IZ. This is the power dissipation across the diode. After that, this is the numerical. So here we can see there are two cases. When first case is that when RL is equal to 1.2 kilo ohm, and the second case is when RL is equal to 3 kilo ohm. So what we have to find? We have to find the voltage VL, VR, IZ and PZ. So first we have to draw the circuit, and we have to find the state of the diode. State of the diode means like this is plus minus 16 volt, this is 1 kilo ohm, and this is first case is 1.2 kilo ohm. So here we can find the value of V, that is 1.2 plus 1 multiplied by 16. So 1.2 and 2.2 multiplied by 16. So we can find the value of this, and by solving, if it comes greater than 10 volt, if this V is greater than VZ, then output will be equal to VZ. So we can see here we have calculated the value, that is coming 8.73. So 8.73 is less than 10 volt. So the diode is in off condition, and in that case the output will be equal to 8.73 volt. Now in this case the value of VL would be equal to 8.73. So VL value is this, VR value we can calculate it by 16 minus this value. 16 minus VL will be equal to this VR. So VR is equal to this. Now diode is not in working condition, so current through the diode will also be 0. So in this condition IZ will be equal to 0, and power dissipation is equal to VZ multiplied by IZ, that is it will be equal to 0. And now this is the second case when RL is 3 kilo ohm. So here we will substitute this 1.2 with a 3 kilo ohm, and by solving by putting this 3 kilo ohm we have obtained 12 volt. Now 12 volt is greater than the VZ, is greater than VZ. VZ value is given as 10 volt. So 12 is greater than 10. So now the VL would be equal to, in this case VL would be equal to VZ. So VZ would be equal to 10 volt. So now here value of this value is 10 volt, and VR value would be equal to 16 minus 10, so it will be 6 volt. Value of current IL is the value, IL is the current that is flowing through this RL. So then it will be VL upon RL 10 upon 3 kilo ohm, that is 3.33 milliampere. And after that IR can be calculated by using this VR upon R. So we can find the value of IR that is flowing through this resistance, that is VR upon R. So IZ is the current flowing through this part. So this IZ would be equal to IR minus IL, that is equal to 2.67 milliampere. So PZ would be equal to VZ multiplied by IZ, that is 26.7 milliwatt. Now this is the second case when Vi is fixed and or RL is variable. So this is the diagram, and this is a Zener diode. This resistance is basically used to limit the amount of current that is flowing through the Zener diode. So here this Vi is fixed, this is fixed, and this is variable. Okay, so this RL is variable and this is fixed. So RL variable means like RL is variable, so your current will also be variable. VL is always fixed. Okay, our target is voltage regulation, means to maintain the constant voltage across the load. it may be the case that your input voltage is varying, or it may be the case your resistance is or load is varying, but you have to maintain the constant voltage across this load RL. So if the RL is variable but VL will be fixed, and VL would be equal to RL multiplied by IL. So this amount is fixed. So if RL is maximum, IL will be minimum, and RL is minimum, then IL would be maximum. So here these are the cases, and here VI is fixed, so amount of current that is passing through this IR, it will also be fixed, it will not be varying. Okay, so we can find the value. Now we can find the minimum value of the resistance RL minimum, which is required for the, so that diode may become in the breakdown region. So we know that the voltage across the diode is equal to RL upon RL plus RS multiplied by VI. So this voltage must be equal to Vz or greater than Vz. So if it is equal to Vz, in that case minimum value of resistance will be required. But this much amount of minimum value of this resistance must be required, so that the output voltage, so that this V voltage must be equal to Vz. So so by this equation we can find the value of RL minimum, and this RL minimum will be this. By using this expression we can cross multiply this and we can obtain the value of RL minimum. So RL minimum is this. So IL max will be Vz upon RL minimum. Vz would be equal to VL. So here it will be Vz upon RL minimum. And now RL max. Now we can find the different equations also, like IR from the circuit we can see IR is equal to IZ plus IL. So if it is IL max, here it will be IZ minimum, and if it is IZ max, it will be IL minimum. Okay, so that their sum must be equal to IR. So this will be the equations, three equations. So by using these equations we can find the value of IL minimum. IL minimum is equal to IR minus IZ max. So now IL minimum can be calculated from this equation, and this equation can be obtained from here, because we know IR is equal to IZ plus IL. So this IR is fixed, only IZ and IL are variable. So if IL is increasing, IL max, so this IZ should move towards the minimum side. So this would be equal to IZ minimum plus IL max. So and this IZ max plus IL minimum. So here we can calculate the value of IL minimum, and from this IL minimum we can find the value of RL max. RL max would be equal to Vz upon IL minimum. Okay, now we can find the value of VR also. This VR would be equal to this Vi minus this VL, or this VL or this VL is equal to Vz. We can also write Vi minus Vz. So this is the numerical that we can solve here for the network to determine the range of RL and IL, that will result in VRL being maintained at 10 volt. Okay, so we have to maintain this voltage at 10 volt. VL is given as 10 volt. For the network, determine the range of RL and IL. So we have to find the range of, that is we have to find the RL minimum, RL max, IL minimum and IL max. So for RL minimum there is a formula that Vz is equal to RL minimum upon RL minimum plus R multiplied by Vi. So here RL minimum, we have to find the RL minimum, and here we have given 10 volt. So Vz would be equal to VL. So that means 10 volt is Vz, and RL minimum upon RL minimum plus R. R is 1 kilo ohm. and Vi is given as 50. So here by solving this, like 10 RL minimum plus 10 is equal to 50 RL minimum. So 10 is equal to 40 RL minimum. So RL minimum is equal to 10 by 40. 10 by 40 kilo ohm. Okay, so this much amount of RL minimum is required in this case. Okay, now we have to find the value of RL minimum. We have RL minimum, so we can find the value of IL max. IL max is equal to VL upon RL minimum. VL is about 10 and this is about 10 by 40. So it will be 40 milliampere IL max, and IL minimum will be equal to now we can find the value of IL max is there. We can find the value of VR. So VR would be equal to 50 minus 10, 40. So IR can be calculated as 40 upon 1. Okay, so here it must be equal to 50 minus 50 is given and here 10 is given. So 40. Okay, resistance is given 1 kilo ohm. So this is 50 milliampere. IR, this is this much. So now we have to find the we can calculate the value of IL max. So IL max is there. We have to find the value of IL minimum. So IL minimum formula is IR is equal to IL minimum plus IZ max. So IR is our 40, IL minimum we have to find, and IZ max is given 32 milliampere. So IL minimum would be equal to 8 milliampere. So we can find the value of RL max. RL max can be calculated VL upon IL minimum. So 10 upon 8 kilo ohm is the RL max. So RL minimum we have calculated 10 by 40 kilo ohm, and this would be equal to 10 by 8 kilo ohm, and IL max is 40 milliampere and IL minimum is 8 milliampere. So these are the range that we have obtained for the first part, and determine the maximum wattage rating of the diode. So maximum wattage rating would be equal to IZM is given 32 milliampere, VZ is given 10 volt. So we can calculate the maximum wattage value, that is IZ multiplied by VZM. IZM multiplied by VZ. Okay, so this is the third case, variable VI and RL fixed. So here this is the third case. Here our VI is variable, this is variable, and this is fixed. This RL is fixed. Since RL is fixed, so IL would be fixed, because our target VL is always fixed. Zener diode is basically used as a voltage regulator. So our main target is to maintain the voltage across the RL as constant. So VL is always fixed in each cases. Either it may be case 1, case 2 or case 3. It will always be fixed. So VL is fixed and here RL is fixed. So VL is equal to RL multiplied by IL. So VL is fixed, RL is fixed. So IL automatically will be fixed. So here all the three factors are fixed here. But here VI is variable, so it will be varying from VI minimum to VI max. So that's why the current flowing through this supply VI, that is IR minimum and IR max, it will be also varying. So first case is that we have to find the minimum value of the supply that trigger this Zener diode, so that the diode will come in the breakdown region. So that for that purpose we can find the voltage across the diode, and the same formula is there, RL plus R multiplied by VI. So in that case V minimum, VI minimum would be equal to, sorry, this is VZ. VZ is equal to RL upon RL plus R, and this will be the minimum value of the input signal. This is the minimum value of the input signal that will be required so that the voltage across this diode would become equal to Vz. Because if the voltage across the diode will become Vz, then only it will be triggered and it will be replaced with the plus minus Vz volt, and it will be operating as a voltage regulator. So from this formula we can calculate the value of V minimum, and that value will be like this. This is the value of the V minimum. Okay. After that we can find the equations like we know IR is the sum of IZ plus IL. So here IL is fixed. So if IR is maximum, in that case IZ will be maximum, and if IR is minimum, in that case IZ will also be minimum. So these two equations will be valid in this case, because IR is equal to IZ plus IL and IL is fixed here. So IR max and IZ max will be there, and IR minimum and IZ minimum will be there. Okay, so you here we can see VI max would be equal to VR max plus VZ. So this formula can be used for calculating the maximum voltage of VI, and this numerical can be solved like in the previous cases. We can use the formulas that we have discussed in the last slide, and these are the applications of the Zener diode. Zener diode can be used as a voltage regulator. It has been used for over voltage protection, used in clipping circuits, used to shift the voltage. Thank you.